Hello everyone, so this is our tolerancing project on the battery drill holder. And this project focus on the battery and the battery holder that are mating part. And this mechanism ensure that the battery is securely locked into the drill housing, which is crucial for the maintaining consistent power and enhancing safety during operation. And here is the overview of the assembly that includes both parts. There's a battery holder and the battery. And we also made a small animation on how this entire assembly works. So both of the battery holder and the battery latch can slide in and out just like that.
Tolerancing. So the purpose of tolerancing is to ensure precise manufacturing and assembly of snap fit latch in the battery holder, maintain functionality and reliability under operational stress. Critical dimensions with tolerance. The lacking tab height is plus or minus 0.1 millimeter, width 0.2 millimeter, and thickness is 0.05 millimeter. Flat tolerance, contact surface is 0.03 millimeter. And next slide. Parallelism is the housing latch, and the battery housing is 0.05 millimeter. Positional tolerance is alignment of the lead relative to the house, 0.1 millimeter. And it is critical to use material that resists wrapping and account for shrinking during manufacturing, particularly in injection modeling. These considerations are vital to maintain precise in the final product.
This is a detailed drawing of the battery holder that shows all the important dimensions and angles that allow the battery to connect to the holder. Here's the GD&T for the battery. The three places this can be applied to in the battery are the locking notches, terminals, and guiding rails. For the terminals, the battery must align with the contact points in the holder for electrical connection. For this, there is a positional tolerance relative to the guiding rail datum. To ensure the terminal surfaces are flat to maintain contact without gaps, there is also a flatness tolerance of 0.5. The guiding rails are a feature that ensures alignment with the holder during insertion. There is a parallelism tolerance of the top rail relative to the bottom guide rail. Also, to make sure the battery slides smoothly through the holder slot, there is a surface profile over the entire rail surface.
Applications of GD&T battery holder. The three datums A, B, and C fully constrain the part by restricting all 6 degrees of freedom. Datum A restricts movement across the y-axis and rotation across the x and z-axis. Datum B constrains the z-axis and rotation across the y-axis. And datum C restricts movement across the x-axis and serves as a mating interface for the battery. By preventing translational movement in the x-axis, datum C ensures proper alignment and engagement with the mating part. Using these datums, we can evaluate tolerancing requirements for each specific feature. Using these datums, we can evaluate the tolerancing requirement for each specific feature. For the slot on the right, precise control for alignment and fit is necessary. So we can either choose between a true position or profile tolerance. In this case, profile tolerance is better because we really want the size and the shape to be perfect so that we don't have bumps in the for the spring, and it's all smooth so it can fit in easily. A true position isn't really necessary because the slot is relatively big compared to the entire piece of the entire piece. For the rectangular pins on the left, we need to control size, shape, and location. Profile tolerance is the best choice here, as it governs the entire surface of the pins. We could have chosen a true position, but true positions are better for cylindrical pins. But since we don't really care about the z-axis and the z position, we really care about the form and the uniformity of the pins, we actually would want a profile tolerance here. For these pins, profile tolerance ensures a control of their form and alignment, and doesn't over constrain for for testing. Note block. A note block explains what to do if there's a discrepancy in the drawing. It basically tells the machinist, hey, if you don't know what's going on in the drawing, call engineering, we'll explain it to you. It gives the name of the part, and it tells the machinist to check the CAD for tolerances not provided. And it explains new symbols that are not in the GD&T handbook. For example, symbol A to B indicates a surface profile tolerance for all 4 pins because it's asking for surface profile tolerance for the whole set of pins rather than each pin. This is better than specifying a surface tolerance for each pin because that would be 4 different blocks of GD&T, and that's entirely redundant and would cost way too much. This is way more elegant and it's cost effective. Thank you for watching.